All right, thank you, everybody. Thanks, Louis. Been working on for about 10 years now as a graduate student, then as a faculty member, and it's really an enormous project. But now the idea grant that I received was meant to take it to a next level, a next stage that we hadn't previously been looking at. And we've done about 10 or 12, I can't even remember, studies within this larger project. They've spanned high school students, college students, graduate students, postdocs. We've done quantitative sort of survey-based studies, experimental manipulation and performance-based studies, qualitative interviews, mentor ratings, ratings of the quality of students' posters at conferences. We have lots of different kinds of data, longitudinal data spanning several years. Lots of complexity. Despite all that complexity, my goal today is actually to communicate a very simple story, a very basic, almost simplistic story. And that is about this term, women and ethnic minorities. This is a term that's used quite a bit in the STEM literature, and just in case anyone here is not aware, STEM refers to science, technology, engineering, and mathematics fields. Within the research on STEM disparities, the term women and ethnic minorities is used quite frequently, sort of treating these as two mutually exclusive groups. And from an intersectional perspective, this term is really problematic, because obviously some women are ethnic minorities, and obviously some ethnic minorities are women, right? These are not exclusive groups. But the research generally treats them as such. And also, from an intersectional perspective, there's a lot of different ways to look at this co-occurrence of these two social categories. One is to take a real deep approach to look at the meaning that's created and constructed, experienced at the nexus of these social locations. And that's where we plan to go in the future. The other is the more simplistic, just basic sort of social categories, looking at how these two assigned categories intersect with each other in the context of STEM education. That's the story I'm focusing on here. Really, it's a simple story of disaggregation, sort of pulling apart these groups to understand what the patterns are in STEM participation. So we'll start with a graph. I'm mainly going to be showing you figures, lots of bar graphs today. That's mainly what you'll see. This is one. This shows you percent of STEM doctorates as of 2008. A couple things to note about this. One is that it doesn't really matter what I put on the y-axis here. It could be graduates of majors. It could be starting a particular job, whatever. You see the same general pattern of results. So this is number of percent of graduates. And as you can see, there's a lot more graduates who are from white backgrounds than Asian American, or URM, which is underrepresented minority. The second thing to note about this graph is that these three categories have particular meaning within the world of STEM. We talk a lot about diversity of race and ethnicity and thinking about different social locations that people inhabit, but at the national sort of level discourse about STEM disparities, these are the three groups that really matter. These are the groups that are discussed largely at a policy level. Underrepresented minorities include African Americans, Latinos, and Native Americans. And then you have Asian Americans and whites. These are sort of the three ethnic groups within this context. Okay? And one of the reasons for that is because if you look at the proportion of the doctorates earned to the percentage of the US population, there are particular patterns that are consistent across these groups. So in this case, whites and Asian Americans are overrepresented based on their population in terms of receiving STEM doctorates, whereas underrepresented minorities are underrepresented. And that's pretty much, those rates are pretty consistent across African Americans, Latinos, and Native Americans. Okay, so if we look at gender, though, we also see a disparity, right? This is a pretty standard. Again, it doesn't really matter what I put on this y-axis. We'll see about a 1/3, 2/3 distribution in terms of who's participating in STEM. But this is always looked at sort of collapsed across ethnic or racial groups, right? So we look at gender separately from ethnicity. So if you just simply break apart and look at gender within these three groups, you see a different. It sort of shows you a little something about who's involved in STEM. First of all, so you see the white group looks just like the total group. Asian Americans looks pretty similar as well. But the underrepresented minority group, there's less of a disparity. And it's sort of hard to tell, because I have the full range almost here, but it's really half the disparity. It's cutting that difference really in half. So it's quite a difference when you look at these, when you break apart the groups at this level. I also want to bring attention to the Asian American group, which I think is particularly notable here, because Asian Americans are considered overrepresented in STEM, but Asian American women are not. right? So in the intersectionality literature, this is referred to as intersectional invisibility, that the certain intersections of social groups lead to the invisibility of some oppressive experiences that people have, or marginalized experiences that individuals have. So, and this is, in social psychology, there's recent research looking at this phenomenon that we have, not surprisingly, both ethnocentric and androcentric perspectives. So there's one really great study where they asked people to describe stereotypes they have of various groups. So stereotypes of different ethnic groups, and then gender stereotypes. So when you look at gender stereotypes, they found that in gender stereotypes, the types of stereotypes that people give are stereotypes that correspond most to white male and females. Okay? So when we think about gender stereotypes, we're thinking in terms of white gender stereotypes. When we think in terms of racial or ethnic stereotypes, people tend to think in terms of male stereotypes. So sort of their way of thinking, so when you think about Asian American stereotypes, what people do more often is they'll give you the stereotypes that are more consistent with men than the stereotypes that are more consistent with women. So usually we use our dominant referent group to understand a group if we don't disaggregate it. And so that's what's going on partially with the Asian American group. So I'm just moving through all this pretty quickly so I can show you the data, but essentially what we have here are two problems, the way this is treated at a national level. We have two problems. We have an ethnicity or race problem, and we have a gender problem. And they're treated as distinct. And this is something that is really recognized at a national level as being a problem. And Obama talks about it. There are the NIH and NSF both pump a lot of money into science support programs, including on this campus. Ann Hornicle is here from the North Star STEM Alliance. So there's a lot of national attention to these disparities that exist. Okay, but the attention again is at both of these levels, not just not considering both at the same time. Now, because this is a problem that has received some attention, we sort of think about, well, how do we solve this problem? Right? Solutions are what people are looking at. And in terms of outcomes, the two main solutions are performance, sort of ability, succeeding in STEM, and then commitment to a STEM career. So not only doing well in STEM, but choosing to actually pursue that career. Those are two separate components, right? So these are two outcomes that are really prioritized at a national level. And there was a review of research done several years ago to look at what support programs tended to do. What did they emphasize? How did they try to increase performance and commitment? And there are essentially 5 factors that it comes down to. One is authentic research experience. That's probably the most important thing. Having hands-on, direct, authentic research experience. 2 is mentoring experiences, both instrumental and socio-emotional mentoring, so building those mentoring relationships. 3 is community involvement, so things like coming to talks, coming to networking events, having time to interact with other people. 4 is academic support, so tutoring, study groups, etc. And 5 is financial support, so financial aid. These are the 5 main sort of ingredients to success that are widely believed by most people in this area of research and policy making. However, the programs that exist don't necessarily work that well. Some do, some don't. There's really sort of a mixed bag. The amount of return you get for the money invested isn't particularly good. And so NIH put out a call trying to understand why is this work? How do we understand this process? Why is it that these program components lead to these outcomes? Okay, what are the mechanisms, or in psychological speak, what are the mediators, the psychological mediators that lead from these experiences to those kinds of outcomes? Because if we understand the mediators, what's in the middle, we can better understand how to strengthen the programs to be able to lead to those outcomes. So the project that I've been a part of for these 10 years has identified 2 of these mediators. One is self-efficacy, or your personal beliefs about your ability to carry out the work. So do you have the skills necessary to be able to be a science student or an engineering student? So beliefs about your own skills. And then identity as a scientist or a science student. Do you see yourself personally as a scientist, as a science student? Do you have that as part of your identity? And so we had proposed these as the 2 primary mediators that account for the relations between these program components and the outcomes, in that participation in all of these things will lead to a sense of self-efficacy and identity, which in turn leads to higher performance and commitment. And this is something that we've tested this model, again, in a lot of the studies I mentioned, from adolescents through postdocs, and we found consistent results, findings for this model, supporting that these are two very important mediators. They're not the whole story. There are other things in play here, but that these two are particularly important. So I provide all this model sort of as the backdrop to try to understand, this is one model that we have. Many other researchers and policymakers have different models, but the models all have something in common, coming back to my original, where I started, is the focus on women or ethnic minorities, okay? So the models are built on sort of this, thinking about these groups as two distinct groups. And what I want to show you is some data, particularly on commitment to a STEM career. So I'm not going to talk about any of the other parts of the model, but looking at the commitment aspect and how this more intersectional perspective might change the way we think about commitment to a STEM career. And even, I think another layer of complexity that often gets missed in all of this is STEM is such a broad bouquet of fields, right? There are a lot of different STEM fields. Here at the University of Minnesota, we have 3 STEM colleges, College of Biological Sciences, College of Science and Engineering, and CFANS. I'm not going to spell that out. Each of which has its own majors, right? So often STEM is a broad term that's used, but there's a lot of variability within there. So what I'm going to show you then, and I'm hoping then we'll have some time for discussion, is just some patterns looking at, if we look at commitment to different STEM careers, and patterns by gender, patterns by ethnicity, and patterns by gender and ethnicity, sort of what are we losing by looking at a single group only versus what do we gain by looking at both groups simultaneously? So as I mentioned, we have lots of data to look at. I'm drawing just from one sample. These are high school students who participated in a summer science program, a summer science camp in California. So they're mostly sophomores and juniors. The camp is designed to be pretty equally distributed between underrepresented minorities, Asian Americans, and whites. It's not perfect, but it's meant to get a nice distribution pretty equally. You'll notice the weighted high school GPA. So this is a very high achieving sample, right? 4.18 is the average. Very high achieving sample. So these are the kinds of the students that we really expect as high school students probably will go into STEM, hopefully, because they are having the success that they would need to be able to go on. However, we know that that's not necessarily the case. So we can talk about the nature of the sample. I'm not going to go too much into details of here, but if you have any questions, I'm happy to answer them. But again, we have lots of data. What I decided to show you today was just their ratings of what they thought they might major in when they go to college. So in terms of commitment, what are they thinking about going into? What fields are they going into? So these are the ones that we asked them about: biology, medical sciences, math, engineering, computer science, astronomy, chemistry, physics, other science, and not science. Okay, these are the different ones. And so they, from a 1 to 5 scale, it's the full range of the scale. To what extent do they plan on majoring in one of these fields? So looking at the overall results, they all sort of hover around the midpoint because there's a lot of variability in terms of what people are reporting. The notable astronomy is a little bit low, so astronomy isn't one that people are thinking about too much. Computer science is a little bit low, but most are, there's not big differences overall in terms of what people are thinking. Notable is not science is pretty high, considering that they're all at a residential science camp. In terms of other science, you might be wondering what that is. I don't know what that is because we didn't have open-ended, but I know a lot of people are there for video game design. So I think that might actually be what some of that is. But it could be other things as well. So if we disaggregate this just by gender, so just looking by gender first, there's a lot of data on there. Let me just highlight the things that are worth highlighting. We find gender differences in 5 of these domains, in 5 of these majors. Okay, in biology, where we see more women than men, which is very consistent, with enrollment patterns and doctorates, and there is a gender imbalance in biology in this direction, which again runs counter to the aggregate STEM direction models. And then math, engineering, computer science, and physics, we see the sort of traditional gender difference that we would expect. Okay, and these are the fields that you generally, at least in your head, colloquially, might think that you see the largest gender differences in. So just to show these data in a different way, Biology is the one where you see more women, and then the other four, or more women are interested in it, and the other four more men are interested in it. And what's interesting here is there are actually no ethnicity differences in these ratings. So there's no differences by ethnic group. There are only gender differences when you look at them separately, okay? But when you look at them together, it's a little bit different. So when you disaggregate them, you see a pretty different pattern. So here's the aggregate pattern, disaggregated pattern. The white group is basically, the aggregate pattern is perfectly representing the white group, okay? And pretty close to the Asian American, except there's no gender differences in biology for Asian Americans. But in the URM group, it's not quite as stark, right? There's differences in biology still, and it's only computer science. Computer science is sort of the universal truth of disparities, I think, which I think those, like Anne laughs loudly because she knows that's true. So we see already, if we just disaggregate like this, we see different patterns. But let me just show you a little bit more closely so you can see what exactly these look like. And so I'm going to run through a bunch of bar graphs. So this is biology. This is the overall gender difference in biology, so what I already showed. And then if we look, this is the ethnicity difference. There's really no difference. URM's a little bit lower, but that's not a statistically significant difference. These are the gender differences within group. So again, no Asian American difference. And there's a white difference, and the white difference is larger than the URM difference. It's actually about twice as large in terms of the effect size. So we see that the overall pattern best captures really the white pattern, but also it does capture the URM pattern here in terms of gender. Okay, and then there's just the aggregate, or the ethnic pattern and overall patterns to compare. Now if we look at math, again, this is disparity in the other direction, so there more men are interested in math than women. And then again, there's no ethnic differences here. There's, looks, it's not completely even, but there's no statistically significant difference. And if we look at the gender differences within group, only whites and Asian Americans have the difference and URMs do not. So you see there's a little bit of a difference there, but again, not statistically significant. So the difference is smaller. Even if there is a difference, we're seeing a smaller difference for URMs. So once again, the overall difference isn't necessarily capturing the URM difference. Okay, engineering, this is where you have a little bit of a larger overall difference. This is a pretty large effect in terms of the difference. Again, no ethnic differences in participation or interest in engineering, but pretty big gender differences. The white difference is very, very large. That's a full standard deviation, which is a very large difference in terms of interest in pursuing engineering, whereas the URM group is less than half the standard deviation. So it's, the disparity is 50%. Of the white disparity. So again, we're seeing that the overall pattern gives maybe more insights into the white pattern. Here is computer science. Again, there's a big difference, gender difference in computer science. There's no ethnic difference, although it's a slight trend for whites to be a little bit less interested in computer science, but again, not statistically significant. But then when you look at the disaggregated model, you see a gigantic difference, gender difference, in the white group. That's almost 1 1/4 standard deviation. I mean, that's a really large difference that we see there. Whereas in Asian Americans and URMs, it's pretty small. And for the URMs, it's not. This is the one where all three are statistically significant. So we see this gender difference. So you'll remember. Wait, I have one more. I have physics also. So physics, again, there's the gender difference. There's no ethnicity difference, and then disaggregated model. Whoop, what's going on with URM on the end? There's actually disparity in the other direction. And that is not statistically significant, so it's really actually equal, statistically equal. So we're not seeing the same difference in physics, so it's more similar, whereas the overall is capturing the white and Asian American. So I ran through those obviously very quickly, but the broad point is, remember I said, okay, here are all these gender differences, but there's no ethnicity differences. Well, there's only no ethnicity differences if we're not also considering gender differences. It's not actually true. When you take them both together, you actually see fairly different patterns of interest and pursuit. So, I mean, to say there's no ethnic differences means you're just sort of ignoring some of the subgroup variability that exists and that might be important. You're choosing not to look at what those ethnic differences might be. That the ethnic differences themselves might be gendered, or the gender difference might be racialized. We don't really know sort of what people's constructions of those are. We have to do, that's where the deeper level intersectional analysis we can get to try to understand that. But clearly, when you disaggregate these, you do get sort of a different sense of what's going on, where in general, the overall patterns are going to look the most like the white patterns. That's the consistent finding across all of these, including all the ones I didn't show you. Just that's what you traditionally see. And you'll see that in the broader literature too, in part because a lot of samples that people collect and research are going to be disproportionately white. And so if you have more white participants, they drive the analysis more, and then those are the patterns that you sort of think are true. But we don't see those same gender patterns, particularly for underrepresented minorities. That gender might not be operating in the same way in terms of thinking about future plans for college. So just to wrap up, because we're running low on time, this is framed as two problems, a problem of ethnicity or race and a problem of gender. I think what I'm trying to do with this next phase of moving this work is to shift this into thinking about it as one problem, as part of the broader issue, and really think about this from an intersectional perspective. And that's really critical if we want to be advancing models like this that I've been advancing for many years. This model may not work equally well for all those people. And if we want to know how do these work best on those outcomes, it might require us to do these more nuanced models that disaggregate groups based on social location. And even, of course, the problem with this is it's a bit of a Pandora's box, right? You say, well, you have to disaggregate by gender, but then you also have to do it by SES, and you also have to do it by, undergraduate institutions and resources and all that kinds of thing. And I think that's the direction we need to go, because the more we do that kind of thing, the better we can make these support programs to be more effective, because they're more tailored and more directed towards the populations that need them the most. Finally, the other, in terms of disaggregation, this is something I didn't really speak on at all, is that we view the groups as white, Asian American, and underrepresented minority. And I think the Asian American group in particular is problematic because there's a lot of heterogeneity in that group. And there isn't equal success, academic success and participation in those groups. For example, on this campus, the Asian American students we have here, our student body doesn't fit the national sort of stereotype and understanding of Asian American students. Our Asian American students do not outperform our white students on this campus. And they have different backgrounds and different experiences, but that doesn't get included in these kinds of analyses because at an aggregate level, Asian Americans are overrepresented. So I'll just stop there. We can have questions if anyone has any.